First, here are all the parts of the project: a board to use to measure the swing, a ruler, string, an eye bolt to support the pendulum, 2 identical nuts that act as my masses, and all the tools needed to put it all together. It is very important for the calculations that the weights are equal, so I measured them to exactly 16 grams for each of them. Next, I have to assemble the project. This took a little time, so the video will speed up, but the biggest challenge was to make the pendulum arms the same length. The strings must be the same distance from center of bolt to center of bolt to fit with the calculations that are further in this video. I measured it by tying each of the knots to a string, measuring out 20 centimeters, and then tying another string and doing it for the second. I went back again and double checked and got very lucky they were the same on the first try. For the hand calculation portion of this experiment, I followed along similarly to the problem that we did the other day for homework. I set up 2 different equations of motions for each of the different pendulums, mass 1 and mass 2, which are represented by each of the bolts. After I was able to set up the equation, I used small angle approximation to get each equation of motion. By substituting in that the masses were equal in weight and the lengths were the same, I was able to get to the 2 final equations that are shown here at the bottom in the rectangle. Going on, I set up that the response equation was going to be equal to theta times theta 1 times cosine omega t plus phi, and then set up one of those for theta 1 and theta 2. By taking the second derivative of both of those, I was able to get the set of equations on the left. After that, I was able to transform it into a matrix that is seen on the right, and from there, setting omega squared times m times L divided by m over g to lambda, I was able to find the eigenvalues and thus found omega 1 and omega 2. With that, I also found the ratio between theta 1 and theta 2 for the response equations. Using superposition, I added them together to find the response for theta 1 and theta 2 as a function of t. For these 3 trials, I set the theta 1 and theta 2 and each equal to different numbers, shown in the matrices in the middle. For the starting velocities, I set them both to 0 for the entire experiment. These were used as my initial conditions for when t equals 0. Using MATLAB, I was able to solve the system of equations represented by these 4 equations to find values for theta 1, theta 2, phi 1, and phi 2 for each of the initial conditions that I stated above. Here is the MATLAB coding that I used, showing me setting the initial conditions as well as the constants and running through a for loop to solve the equation for the 3 different sets of conditions. In this next set of code, I used the answers that were found above and ran them to find a set of 1,000 values from the time t1 to time t3 seconds of predicted motion for each of the 3 conditions. Then I found from that the max of theta 1 and theta 2 for each set of conditions. These are the ones that I then marked on the poster board that we could compare just eye to eye while the testing was going. You can see that the top nut got pretty close to the predicted MATLAB value for theta 1, but theta 2 did not get as close at all. We are lining up to try to approximate to the purple line. For test 2, I set it up so that theta 2 was now 5 and theta 1 was 0. As we can see in the slow motion version, the theta 1 got close to the red line indicated, and as well as theta 2, but they were both just a little bit short. For test 3, I set theta 1 to be equal to 5, and I set theta 2 to be equal to 10. This would almost act as a normal single pendulum since they are both starting in a diagonal line, but the response is slightly different. You can see in the video that the bottom one reaches and almost exceeds the green predicted value from MATLAB. Theta 1 does not exactly reach it, but is close. During this experiment, we saw slight variation between the predicted values from the MATLAB code that I had written and the values that we got from the experiment. This can be due to a lot of things, such as I neglected air resistance, friction between the board and the nut that happened slightly, and also user error of not exactly having the initial velocities and the forces to be equal to 0. But for most of it, it was pretty close, so good job.